on to part 2 of the Lorentz transformation. Let's remind ourselves what we just did in part 1. Again, Alice and Bob. Alice stationary in this case, Bob moving with velocity v, and each of them have their lattice of clocks synchronized. Now, of course, as we know from relativity, simultaneity, etc., that they would not be synchronized completely, but at time t equals 0, we can set up such that at that instant time as Bob passes Alice, then their clocks agree at that instant, and locations, we'll say, are at that the origin, the 0 point as well. And we showed for an event at some TB, some time TB measured by Bob on his lattice of clocks, and x sub b equals 0 at his origin point. In other words, with him in his cockpit, in his ship, we imagined a flash of light right there, so that means that's x b equals 0. Whatever time that flash of light may have occurred along here, if it occurred at his cockpit, that's where his origin is. Remember, that's his lattice of clocks. Remember the props we used that showed that lattice of clocks. And as far as he's concerned, he's at rest with his lattice of clocks, and that's the origin. That's the xb equals 0 point of the flash. And we showed, given that special case, then, and we know what Bob's time measurement is, we can find t sub a for Alice, what her time would show on her clocks, and x sub a, the location of Bob in terms of her measuring system. Now, what we'd like to do, instead of having the flash right there, as we talked about, we'd like to have a flash occur any place in terms of Bob's system that he measures. And he says hey, I saw a flash of light, an event, something occurred at xb equals something or other, and times something or other by my lattice of clocks. In other words, some xb, tb. And we'd like to find out, okay, for Alice, what would be the x location of that, and what would be the time showing on her lattice of clocks. So in other words, we need some formula. We want to have, given xb and tb, we want to say, okay, xa equals something or other involving xb and tb, and ta equals something or other involving xb and tb. Sort of like what we have here. Ta equals something involving tb. Xa equals something involving tb. Xb does not occur in these formulas because, remember, the special case we did had xb equals 0. Now we want the general case where xb could be non-zero. And so we have to figure out, well, some formula, couldn't there be infinite number of formulas that might apply here? We'd like to put some restrictions on this in terms of what we're looking for. And just to give you a couple examples of restrictions. So we're not looking for just an infinite number of formulas. We have to sort through and figure this out. First of all, let's just say we had a formula like this. What if we said, very simple thing, what if xa equals xb squared plus tb or something like that? Okay? Let's just even throw a gamma in there as well. Got some gammas around here. So what if the formula had that form? Given xb and tb, multiply all this stuff together, add it together, and that would give us the value for xa. Note this can't be the right formula because the units have to match up. xa is measured in meters or whatever length unit we're using. xb squared here, if we're using meters, that means this is in meters squared. You can't have meters over here and meters squared over here. And then gamma is dimensionless. It has no units. T is in time. It's seconds. And so I'm adding meters squared plus seconds. You can't do that. It doesn't make any sense. And so you've got sort of meters squared and seconds mixed up over there, and you have got meters over here. That's not going to work. You can't have a formula like that. So that puts some restrictions on it. In other words, whatever the formula is, the units for this one over here have to be units of length. And the units of this formula, whatever it is, have to end up being units of time there. So we can't have something like that. Another thing, I just actually erased our formulas here, but when xb equals 0, then I have to get my two equations from part 1. So these more general formulas have to reduce down to the part 1 equations in the case of xb equals 0. So that would be another restriction on it. But that still leaves a lot of possibilities. So we're going to it's not really a derivation here or a rigorous argument, but we're going to try to motivate a certain form of these formulas that we're going to have here to make our life a little easier. And here's the basic idea. If I'm writing, XA equals whatever over here, and TA equals something over here involving XB and TB, I can't have any XB squareds or TB squareds or square roots or stuff like that over here. Okay? I just have to have XA or XBs and TBs in either case. Why might that be a restriction? If it is a restriction, it's good because it'll really reduce down the possibilities in terms of our formula, as we'll see. But let's just figure out why not? Maybe a TB squared in there, or an XB squared, or a square root, or something like that. Let's consider our clocks here with TA and TB, and let's just say let's let TA equals TB squared. Okay, now I know, as I was just talking about, the units aren't going to work there, so we'll assume we have some other stuff there where we can get the units to work out. In fact, let's do this exactly here. So, well, actually, I don't. We could do something like this. So that's second squared on the top. I need to get seconds here, so I need in the denominator, I'd have to put something that involved seconds there. And so I certainly have a velocity. If I have sort of a, if you just play around with this, if I have a v involved there, velocity is meters per second. So 1 over the velocity is seconds per meter, right? And then if I multiply that just by, let's just say xb here. Okay, so xb divided by a velocity, so that's meters, say, divided by meters per second, gives me units of seconds down here. I've got seconds squared on the top, so the whole thing turns into seconds. Okay, so don't worry about it if you don't quite get the point there. The point being is I could make a formula over here such that I've got seconds here and seconds over there. But to make our lives a little easier, we're just going to assume that we're going to leave aside the dimensions and units for a minute and just say we can do something like this. TA equals TB squared. Just to show that we can't have any TB squareds over here. Why not? Well, let's think about this a minute. Let's say that Bob, okay, so we have TB equals 0, 1, 2, 3. Okay, just some times TB. That means, by the formula we're trying out here, TA would be TB squared. So it's 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay, by that formula, TB equals that, and plug in the values, and we get the TA values there. It's a little strange here. In fact, the point we're going to make is that the distances between ticks, say, on our clocks have to be uniform. Okay? Note the distance here. I've got 1, 1, 1. Here I've got 1, 3, 5. Okay? Why do they have to be uniform? Well, let's do this argument here. T sub b equals 0, 1, 2, 3. I could just as easily on Bob's clocks, we can also move clocks forward or back again, right? We can set them, we can calibrate them, just sort of like daylight savings time, or sometimes you do, depending on what time zone you're living in, what country you're living in as well, whether you use daylight savings time or not. But very easily you can recalibrate your clocks, set the origin, set the 0 point to whatever you want, and you're measuring elapsed times. It shouldn't affect anything. It shouldn't affect your answers in terms of when you set your clocks, in terms of the elapsed time between one event and another event. So for Bob's clocks, I could just as easily reset it and move it forward a second, so that instead of 0, 1, 2, 3, I had 1, 2, 3, 4. Okay, wouldn't make any difference to Bob in terms of his measurements. But look what happens when you then use this formula and put it into Alice's clocks and her times. Then it becomes, well, this is 1 squared, 4, 9, and 16. So whereas with Bob, the distances between the times between each event, still the same, 1 second, 1 second, 1 second. So I got 1 second, 1 second, 1 second. No change between if I had events at 0, 1, 2, 3 versus 1, 2, 3, 4. Just moving the origin for our time scale. But for Alice, it makes a huge difference that Bob just moved those over, because here I had 1 second between them, 3 seconds, and 5 seconds between those events. Now I have 3 seconds instead of 1 second, 5 seconds instead of 3 seconds, and 7 seconds instead of 5 seconds. So if I have things like TB squared in there and square roots and things like that, it messes up the timekeeping system. We expect that this transformation is such that you may have time dilation, as we've seen, so things get stretched out or compressed, but the distances between the events cannot change. Okay, so if Bob has 1 second between events, it's fine to Alice to maybe have 1.5 seconds between those events, but it's got to be 1.5, 1.5, 1.5 to match up with Bob's 1, 1, 1, or whatever the stretching or contracting factor happens to be. You can't have 1 and then 3 and then 5 and so on and so forth. So I realize that's a little bit of a hand-waving argument. It's not a rigorous argument, but that's what we're going to use here to say that you can't have any TB squares, XB squares, cubes, square roots, anything like that. So what this means is, assuming our little hand-waving argument here, we'll accept that. For our equations is something like this. And actually, let's write TA first. Okay, so it means that TA is going to take this form. It's going to be a so-called linear form. So for those of you who've had some math, either way back when or more recently, not really too advanced math, but certainly a little bit beyond algebra, perhaps, although you get this in algebra as well. All that being said, what am I talking about here? This is what it's going to look like. TA is going to have the form, some capital G, we'll talk about what that is in a second, times XB plus H times TB, and XA, the formula for XA, again given XB and TB, is going to have the form M times XB plus N times TB. And as I mentioned, this is so-called a linear form because the XB's and TB's in the equations here are just XB and TB. You don't have any XB squareds, TB squared, square roots, or anything like that. And what are the G, H, M, and N? Those are just, technical terms, coefficients, but they're just values that don't involve XB and TB. They may involve V and C, and they will, in fact, as we'll see in a few minutes, but not XB and TB. And so it's a linear form because technically these are forms of lines and not parabolas and things like that, and square root curves, et cetera, et cetera. So, and that comes from our little hand-waving argument that the distances between times, and also works for distance as well, have to be uniform when you're transforming from one frame of reference to another frame of reference. It can be stretched or contracted, but it can't change from one to the next as you go along with it, as we saw. Okay, so accepting that, this is our form here. So this is the form of our Lorentz transformation equations that we're going to go with. Now, our final thing we have to do, and it takes a little bit of algebra here, but we need to figure out what G, H, M, and N are. And we can immediately start off with going back to the case if XB equals 0. So we know if XB equals 0 from part 1, we know TA equals gamma TB, our basic time dilation equation for that special case. And we know that XA equals gamma V TB. Those were the two equations we came up with. And as we said before, these equations have to match these for this special case. So if XB equals 0, so this, if we take this and plug it into our equations here, that means, that goes to 0 for this special case. This term goes to 0 for this special case. And we know that XA has to, let's do TA first. TA has to equal gamma TB. So TA equals, this equals gamma TB. And XA, for this special case where x b equals 0, has to equal gamma v tb. So this equals gamma v tb. And lo and behold, immediately you can see what h and n are. And you've probably already seen it. If Ta equals gamma tb and also equals htb, clearly h equals gamma. Right? htb equals gamma tb. So this implies h equals gamma. And for this one, xa equals gamma v tb, which equals n tb in our general form, linear form of our transformation equations. And therefore, we have, this implies n equals gamma v. Therefore, here's what we've got. So the way we got this is we applied our special case, xb equals 0, to those general equations. And therefore, we're halfway there. Because now we can write, our general equations is this. We can write, okay, Ta equals, we still don't know what g is, but g xb plus h is gamma, plus gamma tb, and xa equals m times xb plus n is gamma v tb. So those are our two Lorentz transformation equations. As I said, we're halfway there now. We still need to find out what g and m are. But we found out sort of half the form of the equations. We had the argument that they need to be linear like this. They need to, in the case of xb equals 0, reproduce our part 1 equations. And so we've got that in there. And now in the next video clip, what we'll do is tackle finding g and m. And we're going to go back and use our invariant interval equation to do that and crank through a little algebra and get our final form then of the Lorentz transformation equations.